All right, so we're in section 7.3 now, and as you can see from the title, we're talking about something called trigonometric substitution. So one of your integration techniques that we have used a lot, that we learn all the way back to Calculus 1, is U substitution. And U substitution is where you have an integral where you're trying to evaluate or you're trying to integrate a function that is maybe difficult to find an antiderivative of just by looking at it. But if you take part of that function and you set it equal to some new variable u, so u equals some function of x, this would cause du, by definition, to equal f prime of x dx. You make substitutions using this u and this du in that integrand, and hopefully if you do it well, the result is easier to integrate. It's easier to find an antiderivative for. So we've seen plenty of examples by now where U substitution has been really useful. However, as we've also seen, U substitution is not a sufficient technique to solve every integral that we come across. We've seen how integration by parts was needed for some of the integrals we did back in 7.1. 7.2, we looked at some kind of general trig identities that were helpful for solving, trigonometric integrals. What we're looking at here is specifically integrals that have expressions similar to one of these here. So when we have an expression that involves like a square root of some constant minus an x squared, or some constant plus an x squared, or something similar to that, sometimes in those cases U substitution is helpful, but as we're going to see in other cases, it's not sufficient by itself. So we're going to introduce a new type of substitution that's really mostly helping us with these types of integrands, or integrands that involve expressions that look like one of these somehow. And the trick here is going to be looking at this substitution from sort of a different angle. So again, with U substitution, what we're doing is we're grabbing part of your integrand, which I'm going to call f of x here, and setting u equal to that f of x. U is a function that we set equal to, or u is a variable that we set equal to some function of x, where that's part of your integrand. Here, with trig subs, and more generally what we call inverse substitutions, trigonometric substitutions are a type of inverse substitution. We're actually taking the original variable x and setting it equal to a function of some new variable. And here I'm writing g of t as that new variable, but actually in this section we're going to be using thetas instead of t's for the most part. When we use this kind of a substitution, we have x equals g of t, but then we also have dx equal to g prime of t dt. And so we use these two expressions to make, or these two substitutions rather, in our integral to hopefully make the integral easier to solve. And in this case, this g of t that we're working with in this section is going to be some trigonometric function. In particular, we're going to be using these three for the most part. X equals a sine of theta, x equals a tangent of theta, x equals a secant of theta, and these corresponding expressions here tell us kind of when we're going to use each one of these. Now the reason we want to use these trig functions with these sorts of expressions, notice a sine of theta, for example, would be substituted for the x here. We want to use those because of these identities that help us simplify this type of expression into something that's easier to integrate. And it'll be easier for me to explain that with examples, which we're going to do in a minute. But before we do that, I want to point out one really important thing that we don't have to think too much about, but it is important that it's going on in the background. Like I said, trigonometric substitutions are a type of what's called inverse substitutions. And inverse substitutions are any substitution where x is being thought of as a function of some new variable. Notice that's different than defining a new variable that's a function of x. It's x that's a function of something else this time. In a certain sense, we can think of g of t as an inverse function, so that there's another function that I can apply to both sides of this to sort of cancel that g in a sense. Inverse functions only exist if the original function that you're taking an inverse of is 1 to 1. And you talk about the reasons behind that in an algebra class. We don't really want to go into all of the details for that here, but that kind of presents an issue for us because trig functions are not generally one-to-one. They are periodic functions and they fail the horizontal line test, which is the way that you check if a function is one-to-one, assuming you have a graph to look at. So in order for these trig subs to work correctly, we're going to be making assumptions about the domain of these functions. So for example, a sine of theta, we're going to be assuming that theta lives between negative pi over 2 and pi over 2 every time we make this substitution. And the reason for that is that the sine function is actually one-to-one on this interval. If you were to graph only the portion of this function that lives on this interval, you'd find that it does pass the horizontal line test. But if you sketch out any more of that sine wave, it now starts to fail the horizontal line test. So making a domain restriction here guarantees that we have a one-to-one function here, which is what allows us to do these trig subs in the first place. You'll notice there's similar restrictions placed on the thetas here and here. These are going to be like background assumptions every time we do a trig sub. We're never really going to state these explicitly. So whenever I make a trig substitution, just know that these restrictions are automatically happening in the background. Okay, that's a lot of kind of general talking about this technique without really looking at any examples. So it's going to really help if we just jump into an example at this point. I would like to evaluate this integral right here. It's the square root of 4 minus x squared over x squared dx. Now, if you were given this in previous to this section, what techniques would you be able to try? Well, you could try integration by parts for one thing. It doesn't seem to me that integration by parts would be very helpful. Regardless of how I choose u and dv, I think it's just going to get more complicated each step of the way. I don't think it's going to get simpler. So integration by parts doesn't feel like the right approach. You could try a u substitution. Oftentimes when we've had radicals like this, where you have some expression under the radical, if you're going to use u substitution, we tend to want to grab the entire radicand, the thing that we're taking the square root of. But if I set u equal to 4 minus x squared, then my du would be 2x dx, which means I'd be looking for an x factor kind of floating around in there somewhere, and I don't have an x just by itself. So that doesn't seem like it's going to help very much. So let's try one of these trigonometric substitutions. This table gives us a clue as to what we should be trying here. I have a radical in my integrand that most closely resembles this one right here. Some constant squared minus x squared. 4 minus x squared. So if that 4 there is taking the place of this a squared, then that would mean that a is 2, right? Because 2 squared is where that 4 comes from. So if that's the case, then this is the substitution that I'm assuming I'm going to make. We're going to set x equal to 2 sine of theta. Again, a is 2 in this case. I'm not going to write out the restriction. Remember, that's just an assumption that's going on in the back of our minds regarding this theta. Now, we know when we do substitutions and integrals, there's the variable, but then there's the d of that there's the differential that we have to deal with. So I need a dx to go with this. And again, that's really just taking derivatives. So I have dx equals whatever the derivative of this is, 2 cosine of theta, and then we include a d theta in there. Okay. The nice thing about trigonometric substitutions is because we're doing this in kind of the reverse order of u substitution, x is already isolated here. My dx will already be isolated here, and I typically won't need to do like any kind of solving for things in this step right here. Sometimes we have to do that with u substitutions, but not so much here. So now I'm going to go back to my original integral, and everywhere I see an x, I'm going to substitute 2 sine of theta, and everywhere I see a dx, I'm going to substitute 2 cosine of theta. So this whole thing becomes this. My square root is going to become 4 minus, now x squared, I'm squaring 2 sine of theta, which is going to become 4 sine squared of theta. Okay, in my denominator, I have another x squared. So again, that's going to be another 4x sine squared of theta. And then I have a dx here, which gets this as my substitution, times 2 cosine of theta d theta. Now, at first glance, it looks like we made this much more complicated. It looks more complicated than what we started with, but the main reason we wanted to do this is because we wanted to use this trig identity, or Pythagorean identity, to help eliminate the radical here. And here's what that's going to look like. First of all, notice I have a common factor of 4 here, and if I were to factor that out and then use the square root to take its square root, I would end up with a 2. Okay? So that leaves me with 1 minus sine squared of theta under that radical. I still have 4 sine squared of theta, and I still have times 2 cosine of theta d theta right here. Okay? Notice a few things cancel out. I have 2 times 2, which is 4, divided by that 4. I can eliminate all of that stuff, which is cool. But then I also have 1 minus sine squared, and that's under a radical. So I'm taking the square root of what becomes cosine squared of theta right there. Okay, still have a sine squared of theta here, still have cosine of theta d theta here. Okay, now let's think about what happens next. So I've got, what do I have here? I have the square root of cosine squared. If you take the square root of something squared, in this case, wouldn't I just get cosine of theta? Like the square root and the square, they should be canceling each other, right? Well, yes, but there's kind of a caveat to that. Whenever you take the square root of something squared, you're really supposed to get the absolute value of that thing. So I should be writing the absolute value of cosine of theta here, instead of just cosine by itself. But I didn't bother doing that. And the reason why is because I already know that this cosine of theta is non-negative. The absolute value is not going to change anything if I already know that this is never going to be negative in the first place. And how do I know that it's not going to be negative? Well, remember, we made this substitution. There we go. We made this substitution from the beginning. And we said in the background, we're assuming that theta is between negative pi over 2 and pi over 2. Remember, that's like the fourth and first quadrants of the unit circle. Well, the cosine function is positive, or 0, throughout both of those quadrants, throughout that entire interval. So that's where we get this convenient fact that we don't need absolute values here. It's already going to be non-negative. All right. Let's do a little bit of trig to simplify this. So here I'm going to have cosine times cosine, which is cosine squared. And then I'm going to end up with cosine squared over sine squared, which is the same thing as cotangent squared of theta, d theta, right? Okay, so that's great, but I still, off the top of my head, couldn't tell you what the antiderivative is for this guy. So I'm going to use another trig identity. From my Pythagorean identity, I actually know, let's get that back on screen there, cotangent squared of theta is the same thing as cosecant squared minus 1. Cosecant squared of theta minus 1. This is from trig that we know this. This is cosecant squared of theta minus 1. If you don't remember these trig identities, you'll definitely want to be reviewing them for this entire chapter, really, because we do a lot with trig identities in this chapter. The benefit of converting this integral to this form is I actually do know an antiderivative for cosecant squared. That is going to come out to just negative cotangent of theta. Here I'm going to get minus theta, because that's the integral of just that constant function. Remember, my variable is theta. And then I get a plus c. So am I done? Not really, because even though I've now evaluated the integral, I have everything in terms of thetas here. And I don't want that. I want things in terms of x. That's what I had started with. So I should end with a function of x. Now, you've seen this kind of thing with u substitutions, where if you take an integral an indefinite integral in particular, of a function that requires a u substitution, you end up with functions of u here, but then you just plug in that function of x that you defined u to be in the first place, and then that kind of represents your last step. We're going to do something similar here, except it's a tad more complicated because, again, we didn't define theta as a function of x. We defined x as a function of theta. So what we need to do is we need to figure out, what's the relationship between theta and x in a way that I can use that here. So if I were to solve for this theta here, notice I'm going to kind of go like this. I would have sine of theta equals x over 2. And then if I take an inverse sine, I end up with theta equals the inverse sine of theta. Oh, sorry, not of theta, of x over 2. Ooh, sorry, that's sloppy. That's an x over 2 right there. Okay, so that's good because that gives me a substitution that I can use for that theta right there. I could just plug inverse sine of x over 2 into that theta right there and have negative cotangent of inverse sine of x over 2. But I really don't like that. So we're going to actually approach that differently. If sine, going back to this step, if sine of theta is equal to x over 2, we can use a right triangle to make kind of better sense of that. Let's just draw a right triangle off to the side and assume that the theta that it's talking about right here is that angle right there, okay? Now, within a right triangle, I know that the sine of an angle, sine of theta, is equal to the opposite side over the opposite side over the hypotenuse. Well, notice that my sine of theta here is already equal to something over something. So in this right triangle, if I were to call this x and this 2, then sine of that theta is x over 2. I get this, right? So that's kind of cool, but there's a third side missing in this right triangle. You can find that by using the Pythagorean theorem. It would be the square root of this thing squared minus that thing squared, or the square root of 4 minus x squared, which, wouldn't you know it, we've seen that before. That was part of our original integral. Okay, now, the reason I'm doing this is because if I have all three sides of this right triangle labeled, then I can find any of my 6 trig functions of this angle theta as a quotient of, some pair of these numbers here. So for example, cotangent is adjacent over opposite. That's the right triangle relationship for the cotangent function. So if this is my theta, adjacent is this side that we just found, opposite is x. So putting everything together here, I have negative cotangent, which now looks like this, negative 4 minus x squared over the opposite side, which is x, minus theta, which we decided up here is the same thing as inverse sine of x over 2, a little less sloppy there. And then, of course, you can't forget your plus c. And this right here is my final answer, okay? I don't always recommend doing this for, every single integral you do because it can be really time-consuming, but it is worth, I would suggest anyways, taking a derivative of this to make sure that what we get is the original integrand, right? Because that's how you check if you've done an indefinite integral correctly. All right, I want to try to fit another example in here. So for this one, we want to evaluate the integral of x over x squared plus 1. Now this integral you actually can do with a u substitution. It's not terribly difficult to do. You can set u equal to x squared plus 1, and when you do that, your du becomes 2x dx, which is almost what you have here. So a very small manipulation on that du makes this a much easier integral to do. I want to try a trig substitution anyways. And what we're going to think about with this one is I'm going to go through the trig sub. You on your own, go through the same problem, but do a u substitution. It's good practice. And let's see if we get the same answer by doing that, okay? So coming back to here, the integral that we're dealing with has this type of expression in it, some constant squared plus x squared. I want to use a tangent of theta. That's the substitution that was shown on that table. What's the a in this case, though? Well, a squared would be this 1 right here. So that means a is also just 1. So I'm going to set x equal to 1 times tangent of theta, which I don't really even need to write the 1. I could just say tangent of theta like that. Okay, now let's find dx. Well, the derivative of the tangent function is secant squared. So I get secant squared of theta, d theta. Now looking for where the substitutions would go. Plugging in for all of the x's here, a tangent of theta. I'm going to get tangent of theta in my numerator. In my denominator, the square root of x squared will look like tangent squared of theta. And then I have that plus 1 right there. Okay? My dx is going to become secant squared of theta d theta. So far, so good. Now, my denominator. The whole point of these trig substitutions, just as a reminder, is to use an identity that simplifies the thing under the radical in such a way that the radical actually just goes away. So tangent squared of theta plus 1, we have an identity for that. We know that tangent squared of theta plus 1 is the same thing as secant squared of theta. Okay? That's the only thing that's changing from here to here. Now, when I take a square root there, I get this. So just secant of theta down there. And please remember that technically I would have wanted to put an absolute value here, but I didn't. And if you think back to the previous example, you should be able to justify why the absolute value is not actually needed. Okay, but I'm going to let you think about that. Now I see a secant of theta down here and a secant squared here. I can cancel that with one of those secants right there, giving me the integral of secant of theta, tangent of theta. That's all that's left. But I recognize that, secant of theta, tangent of theta. That's the derivative of the secant function. So this integral, being an antiderivative, is going to be just secant of theta plus c. And once again, we're not done. Because remember, we don't want a function of theta as our final answer. We want a function of x. So I'm going to do the same thing that I did in the previous example. I'm going to set up a right triangle, label one of my angles theta, and then go up to my original substitution, and I'm going to decide how does this theta relate to x within this right triangle right here. It's going to be a little bit more helpful if I take that x and put it over a 1, because we're used to thinking of trig functions within right triangles as quotients of things. So the tangent function I know is opposite over adjacent. Opposite in this case would be x. Adjacent is that 1 that I put down there. Okay? So if I took the tangent of this angle, I would get x over 1, which is what I have here. The Pythagorean theorem, I would do the square root of this thing squared plus this thing squared, which is going to look like the square root of x squared plus 1, which again, notice that that's something that showed up in our original integral. That's not a coincidence that that keeps happening, okay? So what is my final answer here? I have the secant of theta, and I need to convert that into a function of x using this right triangle right here. Well, the secant function is the reciprocal of the cosine function, which is adjacent over hypotenuse. So secant should be hypotenuse over adjacent, or square root of x squared plus 1 over 1, but you don't really need to write over 1 because it doesn't change anything. And then I have plus c. This would be my final answer. Okay, this one's a little bit easier to check by taking a derivative to see if I get this. So if you want to try that, I would recommend it. We have more examples to do, but let's tackle those in the next section, or the next part.